Okay, let's get started. Yes, let's record. Okay, go ahead, Shino.
Yes, so welcome to today's paper reading meeting, and today I'm going to talk about the paper published in Nature Geoscience that is a pre-collisional extension of microcontinental terrains by a subduction pulley. So I think this work is an important complement for plate tectonic theory. The first author is the Urken. He's a PhD candidate majoring in geodynamics at the University of Toronto. And I think he was born in Turkey. And from 2001 to 2009, and he got his bachelor and master's degree at the Istanbul Technical University. And then in 2017, and he became a PhD candidate at the University of Toronto. So this paper is part of his PhD's work. And so let's go to more details of this paper. So let's take a look to our universe and our solar system. So our Earth is the only habitable planet in our solar system. And it has some key characteristics. For example, the liquid water and appropriate composition of atmosphere, and particularly the plate tectonics. Plate tectonics, our Earth is only habitable planet that has plate tectonics. And it's tightly related to the crustal formation and continental growth. And water recycling between the surface and mantle and may have influence on the formation of grid oxidation events and the earthquake on Earth. So plate tectonics is important for Earth. So what is plate tectonics? Let's go to review this theory. So plate tectonics has been proposed in last century, I think more than 50 years from now. And the term plate defined from rheology and mechanics. And the tectonics means the to build. So the tectonics describe that the Earth's surface is composed of rigid plates that can move in relative to one another on top of hotter, more mobile mantle material. So it has some important technical setting. For example, the mid-ocean ridge, where the new oceanic plates generate here.
I cannot hear you. Now I cannot hear you. Yeah, you may log out, log in again. Or maybe you could use your phone to log in.
with现在呢 ？OK， 好
So go ahead.
，OK， 现在就听得比较清楚了。我是从哪里啊？Where should I start from?
Yeah, what is tectonics? Yeah, go ahead.
Yes. What is plate tectonics? The tectonics are defined from the rheology and mechanics, and tectonics means the to build. So plate tectonics means the describe the Earth's surface is composed of rigid plates that are moving relative to one another on top of the hotter and more mobile mantle material. There are some important tectonic setting here, such as the mid-ocean ridge, where the new oceanic plate generate, and the subduction is where the two plates meet with each other with subsequent collision and arc magmatism and back arc rift. And for subduction zone, there include intra-oceanic subduction or the ocean content subduction zone. And in traditional plate tectonics, it describes deformation events on overriding continents or microcontinents, usually attributed to the contemporaneous or preceding collision or subduction, such as the thin collisional terrain extension, and this is the post-collisional extension, such as the back arc extension. But in this paper, it proposed an alternative tectonics mechanism that is the pre-collisional extension or exhumation during the terrain drifted to subduction zone. So it is an important complement for plate tectonic theory. So how did they come to this idea and implement the work? So it can divide it into two parts. The first, the geological observations, and then is the geodynamic modeling. So according to previous studies, such as the Caesar terrain in Western Alps, the geologists found that the Caesar terrain cleared and created the adero-continental margin by Bitcoin, and but the terrain also has experienced exhumation of high-pressure metamorphic rocks, but this metamorphism is earlier than the collision, about the 79 to 62 million years ago. That means that before collision, the terrain has experienced the pre-collisional extension or exhumation. Similarly, geologists also found this phenomenon in the Nephiur and Anatolia terrain. They also experienced pre-collisional extension or exhumation. So the author is not the first one to find this phenomenon. So the most contribution, I think, of the paper is that it used the geodynamic modeling to reproduce and interpret this geological phenomenon. So let's see the geodynamic modeling for detail. So the target of this work is that how the pre-collisional extension of terrain evolve, how such events manifest in the metamorphic record. So this paper used the dynamic modeling sub-alley. So this is a geodynamic code that can solve the two-dimension plane strain deformation of viscoplastic material, and using the arbitrary Lagrangian and Uran, that is the alley techniques. This program or this code is programmed by the Fortune in the last century. And this method is usually applied to material science and computation solid mechanics. And these figures use some parameters of this modeling. Therefore, in order to for us to better understand of this model, just talk more details of the parameters. So the main controlling parameters. The first is the overriding plate type, the oceanic or continental plate. They have different rheology characteristics, so they will have different influence on the pre-collisional deformation. And then is the crystal thickness, usually including the continental crust or the oceanic crust. But for this work, they also only focus on the continental crust here. And the convergence rate. Slab moving and need driving force. So this work usually consider two driving force, that is slab pull and ridge push. And let's see, the convergence rate is 0. Here means that the driving force is the only slab pull. And the convergence rate is 2 centimeters per year, means that the ridge push cost the 2 centimeters per year. And the 4 is the same. And also this paper this work consider the turn widths from the 120 kilometers to 600 kilometers. And here, as you can see here, this is 120, 600, and 450 turn width here. And then, how did the modeling to monitor the extension of excavation? So it tracked the crustal rocks PTT path. So let me explain how did it do this. And so there are 4 tracked rocks here, tracked crustal rocks. The 1, 2, 3, and these 3 tracked rocks located in the low crust, and the 4 just located in up crust. I just take the first, this one, as an example. These tracked rocks near the subduction zone. And let's see the PTT path here. So the x-axis is the temperature, and the y-axis is the pressure. And so this direction means the excavation or extension with the reducing pressure. So for the tracked rocks, in the first stage, with the reducing pressure means that these tracked rocks experience excavation or extension, and then the pressure is become higher, means that and the tracked rocks is buried because of collision, and the pressure continued to be higher, and means that the rocks go to more deep place because these tracked rocks near the subduction zone. So these tracked rocks just go to downside with the subducted plate. So the pressure is continued to be high here. That's the PTT path shows that. And then I talk about the modeling results and discussion. This is example 1 about the turn width is the 120 kilometers, and from the initial state to 5 to 5 million years, and it is 7.1 million years. I've also talked about the tracked rocks 1, and then talk about tracked rocks 2. In the first stage, the reducing pressure means that the tracked rocks experience extension, and then the pressure increasing means that the tracked rocks is being buried because of collision, and then the pressure is reducing because the tracked rocks experience post-collision extension. And for tracked rocks 3, this one. This one is far away from the subduction zone, so it has less influenced by the subducted plates or collision. So the tracked rocks, the pressure is reducing, and did not show Allen, being buried signature. The pressure is continued to be reducing here. I means that it only experienced the pre-collisional extension and the post-collisional extension here. And for tracked rocks 4, because it is located in upcrust. So in the for a short period, it experienced the excavation and then being buried. So the pressure is continued to be higher, and then the pressure is reducing means that it experienced the post-collision excavation or extension. So let's give a short conclusion here. So the 4 low crystal rocks here, all of them have experienced the pre-collisional extension or excavation as drifting towards the subduction zone. But after that, these different tracked rocks undergo different process because their location has different ways from the subduction zone. And for upcrust rocks here, it has been buried and then exhumed during subduction. And then is another example, 2, 3, 4. It has they have different different terrain widths from 450 kilometers and 600 kilometers. These just show similar terrain and similar PDT paths, but with the increasing terrain width here, the pre-collisional extension is reducing. Let's take a look more details of the pre-collisional reducing here. The x-axis is the terrain width, and the y-axis is the pressure drop. The pressure drop means that the maximum pressure difference of the tracked rocks have experienced during the pre-collisional extension. So this direction means the higher excavation. The solid and long dashed and short dashed line show different convergence rates. Let's see for a certain terrain width, 120 terrain width here. The solid line usually shows the large or big pressure drop, means that the convergence rate, when the convergence rate is 0, the only driving force is slab pull, and the tracked rocks will experience more pre-collisional extension. And then with increasing of the microcontinental weights here, the pressure drop is reducing, means that the pre-collisional extension of terrain will reduce with the increasing weights of terrain. That's it to conclusion here. And then also give the extension factor beta, and is calculated from the ratio of the initial and final lithospheric thickness, and it's similar to this one. And they just show the tracked rocks of this one, the center. Now we can see that the beta factors, or the pre-collisional extension just decrease with increasing microcontinental widths here. So let's give a conclusion here. So regardless of type of terrain width or convergence rate, pre-collisional extension or excavation exist during the terrain drifting to the subduction zone. And from we previously discussed above, the vertical slab pull should be the most important driving force for this deformation. And then the extension rate is inversely correlated to the terrain width, as we discussed above. So if the convergence rate is high enough, the collision, the pre-collisional extension or accumulation can be shut off. So as the modeling results show that if the convergence rate is 8 centimeters per year, as you can see, no significant change in pre-collisional extension for the model. And also, the model results show that the slab break-off occurs in part of the subducted terrain here, not just only in the subducted oceanic lithosphere, and it's also consistent with the geological observations in previous studies. In the end, the author just give an example. Use the CISA zone to calculate the PDD path from published data from petrology data, and this is the PDD path, and then he just compared the modeling using the example 3 with the 2.1 centimeters per year convergence rate. So this modeling result may be consistent with the the geological observations by previous studies. So last but not least, I just give a summary of this paper, and I give some comments for this paper. So in this study, this work just proposed new mechanics to interpret the deformation, that is the the pre-collisional extension or accumulation of the terrain during its drifting to subduction zone. So it is an important complement for plate tectonics, and it's also important for field work, because if you observe a deformation or metamorphism in the field, this work provide an alternative interpretation of the deformation or the metamorphism, not just the post collision or syn collision extension of this work. And then this figure shows the distribution of contemporary terrains. If the result of this work is right, so this oceanic terrain may experience pre-collisional extension in the future, but I cannot see how to. But in the future, maybe could be tested. And last but not least, the model results. The geodynamic modeling of this paper use the 2-dimension model, and I think maybe 3-dimension model is more consistent to reality, but 3-dimension model may be complex and difficult to implement. So maybe in the future it will occur the 3-dimension modeling, and it will give a better understanding of the geological phenomenon of this extension or accumulation. So that's all for my presentation today. So thank you for listening here.
Okay, thank you, Chantal. So any questions from other group members?
Yeah, hi, Chantal. Thank you for your nice talk. And I have a quick question: that does the rock type or the component of the rock matter in their model?
I think did not I think did not provide details of the type of the rocks in the model.
Yeah. So do you think that matters or not?
Maybe the type of rocks will influence the extension, because different rocks have different rheology, and I think this paper just consider generally. For example, the continental rocks. I think he just give maybe a comprehensive composition of the tract rocks. Yes.
Okay. How about the you said the PTT, that figure, pressure,
yes,
temperature, and time.
PTT pass. Yes.
Yeah. So the pass they use the component of the rock or not? They just calculate. How do they calculate the PT?
PTT pass because in the modeling, it can the modeling can get the pressure and temperature of the track rocks, and with the time flowing, they got different pressure and temperature. It can
So I could add a little bit. So this is something that I think geodynamics is really good at. So basically, before, so at the initial stage, so they could mark a pixel in this 2D diagram. So they could mark to say, okay, this is a crustal rock. I think that is represented. Actually, I don't know what's their resolution. So is it a 1 pixel? Here they represent maybe, let's say, 0.1 kilometer block or something like that. Then they let it run. So this is solid mechanics. Actually, probably for near surface is okay.
I think it's just a point. I think it's just a point in the dynamic modeling.
Oh, I mean, yeah, I don't know what is the size of each point.
It
because they have
details. I think it did not provide details of the track rocks characteristics because
actually, okay. Actually, we ask about him because I know that in a lower mantle simulation, it's very common. People use 100 kilometer as 1 pixel or 1 block. So they assume that each block is 100 kilometer by 100 kilometer. Then they could call this block, let's say the market, and then you let it run.
No, I think the track rocks will not be 100 kilometers because
I know. Yeah, because it is cross samples. So I'm pretty sure that it has much, let's say, smaller size, maybe 1 kilometer by 1 kilometer. Is possible. So then they could track how that point moves. Actually, this has become something that is really good for not only for this, but also for some geochemical simulation. Because let's say for example, some other groups that is try to see some geochemical signature. So they try to put some, for example, they put some they trace not only about each block, but they could calculate, for example, in this block, it starts with, I'm just randomly make up a number. For example, 2000 ppm of carbon. So then as it goes, then it could calculate, for example, given a certain carbon diffusion rate. So carbon could diffuse outside the block to the nearby block. And with a certain gradient, for example. Then by that, they could calculate what's the carbon concentration in every blocks with time. So as the subducted slab goes. So by this, actually, they could see what's the effects of a certain subducted components to the mantle until it comes back to the surface by volcanic process, because they could also simulate that how does this plume or temperature anomaly that brings some material up. So actually, so I think that geodynamics actually has a lot of very good combination with petrology and geochemistry. And another thing is that actually I'm also interested in. I'm not expert on this, but I'm curious about it because when people do the whole mental conviction, the background knowledge is fluid dynamics. For example, Navier-Stokes equation or something like that. So by this exercise, they do it by the solid material mechanics. And by the time scale they use actually is not perfect. So especially high temperature process with such a long time, several millions of years, I'm afraid that I don't know whether this solid mechanics still fully applies.
Yes, maybe we can ask question for the author. And I see that the AOE and this method is usually applied in solid mechanics. I see the documentation of the method. It proposed that this method has been widely applied in other geodynamic modeling by other researchers. But it also said that this code is not open access, so we cannot maybe we cannot access to this code. Yeah. So let's any other question, or we just move on?
No, thank you.
Yes, we can discuss more about this paper and think and I think it's interesting paper here.
Okay. Okay. It's good for us to read something that is not really petrology, but is something highly related to us. I do hope that everyone could keep an open eye on different research topics. I do think that is a important skill or capability for a researcher to understand a research paper from another disciplinary, and if good, you could propose with a question what they do, and hopefully they could bring some insights into what you do. Okay, I think that's so much about it today. Okay, let's see the speaker on Wednesday. So thank you very much, Chantal. Thank you again for the paper presentation.